Okay. All right, everyone. Let me see. So I'm recording this actually as well. Okay. Well, hello there. Good to be with you again today. As promised, I wanted to talk to you about low Mach flows, and specifically because of the new blood coming into the group who are going to be working with low Mach flows. This is a talk that I gave at NIST in 2017. I did not change it much, and we haven't learned much since then, except for a few things, but this still lays the foundation for the low Mach work that James and I have done in our group. So what are low Mach reacting flows? You hear this word being thrown around every time we talk, every time we're meeting. Oh, it's a low Mach flow, it's a low Mach flow. Projection, scalability, pressure. So I'm going to try to demystify some of the intuitive, and physical understanding of these low Mach flows. So first, let's start defining the Mach number. As you may know already, the Mach number is a dimensionless number. It's a measure of the relative speed of an object or something in a flow with respect to the speed of sound. We usually define a subsonic regime. We say Mach number is less than 1. Sonic conditions when the Mach number is 1, so things are traveling at the speed of sound. And for hypersonic flows where the Mach number is larger than 1, these objects are traveling faster than the speed of sound. Now, I don't want you to put in your mind that this has to be an object. Think of it as information. This could be information propagating in a flow, could be a vortex moving in a flow. Any structures inside a flow. It doesn't necessarily have to be an object like an airplane or a car. Okay. Low Mach. Now, the low Mach regime is a specific regime where we can assume that density variations are loosely coupled to pressure variations. So as you know, in general gas dynamics, you have an equation of state for the gas that relates pressure, temperature, and density together, right? When one of those changes, the density is going to change, the temperature is going to change. Now, specifically for low Mach flows, the assumption is made, the observation first is made that pressure variations do not cause significant density variations. So take a candle, for example, or a flame and go sing for it or play music for it. It doesn't change the reaction, it doesn't change the density changes that are happening due to the reactions. Rather, it is the heat release and the reactions themselves that are causing the density changes, not the pressure. Okay. So reacting flows, clearly there's reactions. I'll give you an example of a candle, combustion, fires, etc. Where do we encounter these low Mach reacting flows? Or in other words, where does that assumption work? It works really well for a good big range of applications. Pretty much all atmospheric flows are low Mach. The Bussinesq approximation that you've probably heard of that is fairly used in atmospheric flows is a special case of a low Mach condition. Sometimes of supernovas in the universe, flares, fires, open fires like forest fires. All of these things can be modeled as low Mach flows, and they are low Mach flows. So where density is loosely coupled to the pressure, or small pressure variations cause no density variations. Some big pressure variations might cause minor density variations, as opposed to true full gas dynamics where a slight pressure variation is going to cause almost the same density variation. Okay, now why do they matter? Why does that assumption matter so much? Because it provides us with a mechanism, with a tool, with a framework to modify the gas dynamics to filter out acoustic waves. Okay, so I need to untangle this statement because there's quite a bit in that. Gas dynamics are the true continuum equations of any fluid flow. So when you consider real flow, you got to start with the full gas dynamics equations. These are the Navier-Stokes equations, so continuity, momentum, and energy equation, and an equation of state. Okay, and whatever else you might be tracking, but those are the foundations, we're going to call them like the true fluid flow equations. Okay. In these equations, although you don't see it, it's hard to see, every term in those equations contains different types of motions. Okay? There are gravity waves, there are acoustic waves, there are Rossby waves, there are also entropy waves, all sorts of things. But what matters the most to our discussion are two types of motion. What we call the bulk flow motion, okay, or the advective motion we're going to call it, and the acoustic motion. These are sound waves, allow sound to propagate. Okay? This is an actual imaging of a speaker done in the 50s showing how waves are propagating in the air. Okay? Now we're going to call the bulk fluid motion a vortex moving slowly in the flow, or like you're looking at a flare or a smokestack, there's like these vortices, these large structures moving. We're going to call that the advective motion. And we're going to assign it a symbol, the velocity, u. These motions, they propagate at the speed of the flow. So when you say the flow is moving at 2 meters per second, this is it. It means that on average, this vortex is propagating at 2 meters per second. The air is blowing at 2 meters per second. Now, acoustic waves, they propagate at the speed of sound. Okay, we're going to call that c. Okay, so we're going to think in terms of scales right now. What I'm showing here is the Schlieren imaging of a person clapping their hands. Okay? Now, you probably can't see it really well, but the instant they clap their hands, there are these waves that come out that propagate in the air. And then seconds later, you see the air being pushed between the two hands. So you can see the two types of motion I'm referring to. This one where these little vortices, these little structures come out of here, this is the advective, the bulk flow motion, whereas these waves that are propagating from the sound, the clap, these are the acoustic waves, the sound waves. Okay. This is very relevant, though. This distinction is super relevant to us numerically. Okay? In a numerical setting, when we solve the gas dynamics equations, we take our domain, our problem, and we split it into grid points, grid cells. We discretize, you know that. Let's call that spacing delta x. Don't care about delta y or delta z, so don't ask about that because we're looking at intuitive understanding over here. So assume that the distance, the average distance in your grid is delta x. Now on that grid, like I said, although you don't see it from the equations, but in reality, there are two types of things going on, at least two types of things going on. There's the bulk fluid motion. That's the big vortex that's propagating. That's these little structures coming out from the hand. But there's also sound waves. Okay? These sound waves, they propagate at the speed of sound plus the advective motion, right? Because they're riding on the fluid itself. So there's waves propagating at u plus c in one direction. There's waves propagating at the speed of sound, and there's waves propagating in the other direction, u minus c. Okay? Great. Now the distance traveled by these two types of motions in a single time step, you are familiar with our methods to solve partial differential equations. So we do what we call time advance, time stepping. We solve the equations one time step at a time, one delta t at a time. Now I want to calculate, and I want to start building an analysis of the distance traveled each time step by these two types of motions. For the acoustic motions, assuming that u plus c is in absolute value is the maximum speed at which sound is propagating, then sound waves are going to propagate at u plus c times delta t in a single time step. Right? So this is distance, meters per second times second gives us meters, so that's distance. Now for the advective motion, we're going to call that the gas itself, the fluid motion, that fluid front, that vortex. It's only moving at the advective speed u. So in a single time step, the fluid front moves at u times delta t. Okay? So those are two distances. Okay? Clearly, you could say from just looking at these two equations that if u is much smaller than c, which it is for most daily cases, right, then sound is propagating at way faster speeds, right, on the grid. Now stability, in the traditional sense where your solution is not going to blow up using an explicit method, and this is was the foundation of this entire discussion, stability dictates that you cannot move information on a grid by more than a single grid point. So in a single time step, the fastest information in your solution cannot move more than one grid point. Mathematically, this means, this puts a strong restriction on the time step. It says that your time step is smaller than this value. And what is the fastest information propagating in our flow? It is the sound waves, okay, at u plus c. So we cannot move more than a single grid point in a single time step. The fastest information cannot move faster than that. Okay. I want to spend a minute on this graph. It took us quite a bit of math to get this graph, but what I'm showing here is on the y-axis, I'm looking at the number of time steps it would take to advect the fluid front, the vortex, not the acoustic waves. Okay? Remember, we're moving at the acoustic wave speed because they're the fastest, right? But I'm interested in the fluid. I'm interested in that vortex, how it's moving. Remember, because the flows we're interested in, sound waves don't affect the fluid, that vortex, that much, right? So if I were to plot the number of time steps it would take to advect the fluid front, the advective front, the vortex, by a single grid point, one grid point, as a function of the Mach number, okay, I get this plot. At Mach number 1, I need 2 time steps to move a single grid point. Why? Because the fluid is moving at the speed of sound, so you get 2c in that delta t or delta x over 2c. So you can move. You need 2 time steps to move by a single grid point. Okay, great. But we're not interested in Mach 1. As you go to smaller Mach numbers, 10 to the minus 4, you need 10,000 time steps. 10,000 time steps to move that vortex that you're interested in by one grid point. You're going to be a skeleton by the time that simulation ends. Okay? All in this time, though, the sound waves are propagating at one grid point per time step because that's your stability condition. You need to move. You cannot move the fastest information more than one grid point. So if we move the acoustic scales one grid point per time step, what happens to the advective scales, to that vortex, it's going to take 10,000 time steps, 10 to the minus 4. 10 to the minus 3 is going to take 1,000 time steps. Well, that's insane, right? Especially that in this entire range of Mach numbers, we really don't care about acoustic waves. So why are we computing them? In a way, like we're bound, we're stuck to compute the fastest information in explicit methods, of course. We're bound to compute those fast information. Okay. In low Mach, like I said, U is much smaller than C because the Mach number is small. Yet the stability is dictated by the acoustic waves, U plus C. What we want the stability in low Mach problems to be dictated by the speed U, by the advective speed. Okay? But that's a problem because the full true Navier-Stokes equations, the gas dynamics equations, they have in them everything, all sorts of waves, including acoustic waves. So if you're trying to solve them, you are bound to resolve those acoustic waves. You can't, there's no way out of it unless you use the low Mach assumption, the low Mach toolkit, and you mess with the equations a little bit. Okay? Low Mach models give us that ability. Okay? Here's a simulation we did in our code a few years ago, 2017. Apparently, I still have my username here. Okay, so this is a heated blob of air in a gravitational field in a room. Okay? This one uses the full gas dynamics equations, and it is stepping at the acoustic timescales. Okay? This Mach number is about 10 to the minus 3 for this problem. So every 10,000 time step, every 1,000 time steps, I move this bubble by a single grid point. Okay? Yet pressure waves are going back and forth, no problem. This simulation took 5.8 hours, let's say 6 hours. Okay? This one, same problem, as best as we could make it similar, but using the low Mach assumption. And it took 58 seconds, so let's see. So clearly it's going to rise, okay, because it's heated. And look at that. Both quantitatively and qualitatively, they are similar. Now you see some structural differences between the two, because this has to do with spatial discretization. Some types of spatial discretization we can use here, but not here, okay? So it leads to some of these structural changes. But did we lose some information? Yeah, we lost a little bit of information, but at what cost? Look at this, 58 seconds, less than a minute, okay? Barely have time to go drink water, come back, and the simulation is done. So this is what we want. This is a great way out of this, okay? So how do we derive them? There are numerous ways of deriving the low-Mach equations or doing simulations in the low-Mach regime. You could take incompressible algorithms, which are actually a special case of the low-Mach problem. These are like what we call pressure-based methods, pressure correction, projection methods. Or we can take fully compressible algorithms and precondition them, what we call precondition, to filter out those acoustic scales somehow, and then get to the low-Mach regime. In our group, we have strong expertise in pressure-based methods, some expertise with density-based methods. We have something working, but not fully to how we like. So we're really focused on pressure-based methods, okay? I'm not going to go through the details here. I want to get to the actual derivation. How do we filter out the acoustic waves? Actually, I'm not going to do the derivation. I'm just going to show you the result, okay? That's something that we could do offline, look at the derivation, and we're still trying to understand that, actually. So if you take the full gas dynamics equations, you have continuity, momentum. This F term symbolizes convection and diffusion, nonlinear convection and diffusion. And you have some species or energy transport, okay? We're just going to call that phi. You could have just an energy equation, or energy and species, or you could have a representation of species with a mixture fraction. Okay, it just represents a standard scalar transport equation, and then you have an equation of state. So clearly, with the equation of state, you need to solve an energy equation, so that's a given for this problem. Now, how do you filter out the acoustic waves? We were talking about this yesterday. There are different ways of doing it. One popular way is what we call single-scale linear perturbation problem. So what we do, we take these equations. Like I said, the density, the pressure, the velocity, they all in them contain information about acoustics and other things. So we say, okay, let's split it. Let's explicitly separate the non-acoustic portion from the acoustic portion. And let's do some scaling. Turns out that all the acoustic terms, they are scaled by the Mach number, okay, multiplied by the Mach number. And as the Mach number goes to 0, those terms become successively lower in magnitude compared to the other terms. So we neglect them. That has the effect of filtering out those waves. Now, when you do this, look at that. You get almost the same equations. These are the low Mach equations. They look identical, but they're not, because they're only solving the non-acoustic portion of the equations. Now, for continuity, well, they're the same. I have a subscript 0 over here. This 0 indicates the non-acoustic portion of the density, okay? Then you go to momentum. If you look at momentum, U and rho and F, they're all the full terms, including acoustics and non-acoustics. They have 0, 0 over here, but look at the pressure now. The pressure here, this P2, is the first non-acoustic, or the second non-acoustic term that ends up showing in the equations. There's a P4 that is actually the acoustic term that we neglect and we don't solve for, okay? However, now, you no longer have an equation of state, because P0 absorbs that initial kind of background field and is only a function of time. It's no longer a function of space, so there's no more equation of state anymore. So you've eliminated that equation of state, and instead substitute, or you eliminated the dependence of the density on the pressure, and instead now your density is only going to be a function of the other thermophysical state, temperature and species transport, okay, through this equation. Then you take these equations, you do the traditional projection to solve them. However, now your dilatation is no longer 0, because for variable density flow, div u is not 0. There's volumetric. We're still changing the density. Remember, there's reactions going on. There's it's a fire. There's a supernova. There's density changes, except those density changes are not caused by the pressure. They're caused by energy release and species and things mixing with each other. Okay, so how do we crack this problem? It took us a few years to figure this out. Again, we have some papers about that, our algorithm that we have in our codes. So we do a bunch of things, we do all the math, and then we end up with a dilatation constraint for low Mach flows. Now, for constant density flows, incompressible flows, div u is 0. There's no dilatation. A fluid volume has to remain the same, a fluid element. Whereas when you have reactions, then that volume is going to change, okay? Because there's reactions and there's heat release, etc. So this is our model for low Mach flows with dilatation. It's not very complicated. It has density changes in it and coupling of the density to the scalars. Remember, I said that the density is still being changed by temperature, mixture fraction, or other species. So you cover all of that through this term. Then you have a diffusive flux term over here. That's a very important term. And we observed sensitivity, order of accuracy to this term. If this term is 0, we recover the constant density case. But when this term is no longer 0, we notice that we don't necessarily recover order of accuracy, but that's a discussion for another time. Anyway, and then you have source terms from the scalar transport for the continuity equation and also density over here. And then now for the pressure, if you've done CFD and constant density flows, you would have a Laplacian over here of the pressure, just del squared P equals something. Whereas now you have density variation, a variable coefficient Poisson equation for the pressure, and has this nasty right-hand side where you can just plug in div u and put it over here. Anyway, so here's what our algorithm looks like. We first advance the scalars, so we're transporting scalars in time. This is a forward Euler method. We first advance the scalars in time. Each scalar, we go through temperature, species, mixture fraction, etc. We advance them in time, and then we use our new equation of state, which couples remember, density is still coupled to the scalars. So that's given by an equation of state determined by the chemistry you're dealing with, or the type of reaction, the type of mixing you're working with. So you have to solve that equation of state. Given rho phi I at n plus 1, from that you have to extract rho n plus 1 and phi n plus 1. Then you go to momentum. You do the standard projection procedure. You solve for the pressure. You update, and you move in time. Okay, so some pros of our method: it can deal with arbitrary equations of state. It recovers the incompressible limit, which is very useful. That's the degenerate condition. It can deal with crazy density ratios. We've taken it to density ratios of 10,000. So you're talking of F1,000. Sorry. So you're talking like mixing of air and water. Okay, so that's a variable density flow. It automatically computes a consistent divergence constraint, this div u n plus 1. But the limitations or the cons is that it has a variable coefficient Poisson equation, or this div 1 over rho grad p. That's expensive. You have to recompute it every time step. It's first order in time. We couldn't take it to higher order. We think we could take it to second or third order, but we've shown consistently that it doesn't converge at higher order. It's made for structured grids. It will be interesting to take it to unstructured grids, and still requires a global linear solver, just like all projection methods. Okay, so it is a projection method. Anyway, I have some results about our method. I'm not gonna go through the details of those. I don't think they're very useful for this discussion. I just wanted to kind of give you a gist of what the low Mach regime is. These are some simulations done with our low Mach model. This is the problem I referred to with the air and water example. It's called a dam break problem. You see? Okay, there you go. There's like a bunch of water, and then it just flows down due to gravity. Clearly, we don't have surface capturing and droplet capturing, but it does a great job just with the simple mixing model. Okay, and with that, that's what I have to talk about low Mach flows. Thank you.
Cool.